Okay. All right, so now we are ready to start the course. First, we're going to look at the 1D elastostatics problem so that we gain some knowledge. Everything we do in 1D is going to help us to understand what's going on in 2D and 3D. In fact, it's the same thing in higher dimensions. So that is why we look really very carefully at the 1D example. If at any point I go too fast again, please interrupt me. We're going to answer questions. Those are actually very useful, again, later if you have to look at these videos online. So what I have here is just a bar. You know, a bar is a structural element that can take only axial load, compression, tension. You may be all familiar with this already from previous courses. So in many ways, what we're going to do now should be a review of what you have taken from previous courses, right? So if you see the bar element, you have your cross-sectional area. This doesn't have to be constant throughout the bar, so we are not going to assume that it's constant. You have a load per unit length. We call that B. Just to be consistent later on when we go to higher dimensions, we call this a body force. You have a distributed spring, so you can assume that this bar is restricted laterally by some spring that is distributed along the length. So in a way, if you have a positive displacement of the bar, that force is going to be contrary to the movement, so it's going to have a negative direction, right? And then we're going to assume that the bar behaves linearly. We assume that it's therefore Hooke's law, and that therefore strains are related to stresses linearly as well. So very simple. So if we want to just take one piece of that bar, and we call that delta x, and we want to do the equilibrium of that bar, so I'm missing here a couple of forces. Let's call this guy here n of x plus delta x. And this is going to be n of x. And we just do equilibrium in one direction, in the x direction. Well, what you see is that you have n of x plus delta x minus n of x plus b multiplied by delta x minus k u delta x. As we just said, there is a distributed spring per unit length. So then basically when you multiply that by the delta x, you get in a way the total spring that is acting on that infinitesimal volume of the bar, and then times u will return the force, and as you see, it's a negative because of what we said, it's contrary to the movement, right? So then all of these has to be equal to 0. Okay. Now if we just we divide this expression by delta x, and we take the limit as delta x vanishes, then you are left with this expression. Some of you may immediately recognize that this term here is going to be the derivative, plus b minus ku is equal to 0. And so we have the variation with respect to x plus b minus ku equal to 0. And what was the axial force in this case? Well, the axial force, as all of you know from previous courses, can be written as the stress times the area, the cross-sectional area at that location. And because of Hooke's law, this is the modulus, Young's modulus times the strain times the area, and this is equal to our expression du dx. And so our final equilibrium equation becomes the derivative with respect to x of dA du dx plus b minus ku equal to 0. And this expression which is the expression of equilibrium of an infinitesimal piece of the bar, basically has to be valid throughout, right? Otherwise, we don't have equilibrium. So then I'm going to say that this has to be valid for all x in the bar that I call omega. Normally, this is the way you define a subset of interest that you are analyzing. So omega is usually your domain, and I'll get a little bit mathematical in a minute to talk about the endpoints of the bar, which belong to the boundary of that open set. Yeah, you have a question? Yeah, so in the case that you have this spring is distributed, right? So you can think about Ku as being the force of a spring that is acting at a point. Now, if I want that same spring to be distributed, I have to divide that by the length of the bar. So the moment I do that, then it becomes not a real spring, but in order to get the equivalent real spring, I have to multiply by delta x, and then it becomes the notion that you already have, that is just Ku. Okay, so we have our differential equation. So this equation, as you can see, is a second order ordinary differential equation. And can we solve it at this point or not yet? Who can tell me? Yeah. If you see the problem does not deal with time, so initial conditions are not necessary, but what do we need? We need the boundary conditions. So because it is a second order differential equation, how many boundary conditions we need? 2. Those 2 boundary conditions are going to give us our integration constants, and after we define those, then we can obtain the actual exact solution to this problem. And as you would expect in 1D, everything is very simple, but as I said earlier, when we go to higher dimensions, to obtain the exact solution is going to be very hard sometimes, and so we have to rely on approximate methods like the finite element method. Okay? So then we said we need 2 integration constants. That are provided by boundary conditions. Let's talk about boundary conditions. Who can tell me a little bit about what type of boundary conditions I can apply to this bar? You all know this. Yeah. Okay, so you can prescribe that. Yeah, that is one. And there is no angle here. Remember that this is a bar. It's only displacement along the x direction. But we can prescribe the displacement, and this is what usually it's referred to as essential, more mathematical, Dirichlet boundary condition. And this acts on the primal field. Yeah, or the primal variable, which for this case is the displacement. And normally what we say is, well, this type of boundary condition is usually expressed, well, what I want to do is to prescribe u on gamma u, and I want this to be some prescribed value. So this u bar is just a function that I want to prescribe at that location. And gamma u, normally what you find in finite element papers is that gamma u is the part of the boundary where those conditions are prescribed. In this case, Dirichlet boundary condition. And this is, I'm going to get a bit mathematical here, but it's just simple. It's very simple to understand. what we said is our bar is omega. Okay, omega is our bar. That is a subset of the scalars, right? The subset of the real. This is where I have to make sure that my equilibrium equation holds. But this is actually an open set. That omega does not include the endpoints, or what we refer to as a boundary. Yeah, so stay with me a bit. It's going to get a bit mathematical, but you will see that it's very simple. So if you just take the closure, which is not usually denoted like that, you put an over bar on your open set, and then you denote by that the closure of that open set. That includes already the boundary. So usually, mathematically, the way you define the boundary, well, if I take the closure of that open set and now subtract the open set, what I get is the boundary omega. Yeah? And what? Huh? The slash is set minus. Sometimes you can also find it written just by this, by subtraction. But mathematically, that slash means subtraction. You are subtracting a set from another set. So very simply, what this means is just that if you take the domain plus the boundary and you subtract the domain, you get the boundary back. But this is the way it's usually defined. You define the boundary in finite element papers. And so this boundary can be split, right? Gamma can be split in gamma u and in gamma t if you are applying interactions. We're going to see that in a minute, right? But this is the way you mathematically describe it. It's very, very simple. So who can tell me what other type of boundary condition we can apply? We can prescribe the force, and this is called the natural, or more mathematical, Newman boundary condition, and this is acting on the dual variable. Yeah, and in this case is the actual load. Yeah, and the way we usually denote this, well, the force is actually, we have it here, right? It's EA du dx. So what we're doing is we're prescribing EA du dx at the part of the boundary gamma t, which is again, gamma t, we use this symbol to denote the part of the boundary where you are applying the natural boundary condition. And this is equal to some value that you want to prescribe. So remember that when I do a bar u, that means that the function that describes the prescribed displacement, when I use bar n, this is used to denote the prescribed actual load. Okay? But I'm missing something here, and we have to multiply this by n, and this n is either -1 or 1, depending on where you are applying this boundary condition. And we're going to get there in a minute. Okay, so we said that n is either -1 if you are we're acting on the left, or +1 if we're acting on the right, and this is just because of the convention that we use, that whenever this bar is compressed, right, if you apply a positive force on the left end, that is going to cause compression in the bar, and that positive force produces a negative strength. So this is because of our sign convention. In higher dimensions, normally this boundary condition is actually multiplied by the normal to that boundary to provide the same effect. Okay. So we have Dirichlet boundary conditions. We have Newman boundary conditions. What other type of boundary conditions we can apply? Yeah, we can apply a combination of those, right? So this is the last one. So we have mixed which is also called Robin boundary condition. And so we are going to use the same. We're going to combine these two, and I'm going to use the gamma H symbol here to denote that part of the boundary with mixed boundary condition. And then this is equal to H U minus U at gamma H. And H in this case is also acting as a spring, right? So if you look at the book chapter in Nota Bene, you basically have that. Let's make a drawing here. So if this is your wall, that wall is connected to the bar through a spring. And we call this a spring constant H because this type of boundary condition is used a lot in heat transfer, and in that context, this type of mixed boundary condition, H is the heat transfer coefficient. So we keep the same notation to simplify things when we move on to the next type of equation. But what is important to note here, so we are missing also N here, the same thing applies with the sign. But something to consider with this boundary condition is that as H goes to infinity, what you're actually doing is you are approaching to an enforcement of the Dirichlet boundary condition. Okay, that is basically what's happening. And well, again, we have as I said, the same sign convention. So now that we have seen the types of boundary conditions and we have the equilibrium equation, we are ready to formulate what it is, as I said earlier, called the strong form of the boundary value problem. Right? So whenever you hear boundary value problem, it's just not the equation that you're solving. It's equation plus boundary conditions. And it is called strong because in a way you have to satisfy that equation strongly, meaning at every point in your domain, that equation has to be valid. So if you have an exact solution, right, and you plug that exact solution into your exact equation, it has to be exactly satisfied everywhere. Otherwise, it's not an exact solution. And you have some sort of residual, which is what we're going to find when we use an approximation method. Okay? Any questions at this point? Yeah? Yeah. Gamma T and then gamma H. And normally, something that is important to say before we move forward, what people normally say is these conditions are mutually exclusive, or they are disjoint. That means that at a point, you cannot prescribe two things. Of course, it doesn't make sense to prescribe the force and the displacement allocation. Either you prescribe one or the other, right? And normally that condition, when you read a paper, you're going to find out things like this. You're going to see gamma U intersection gamma T intersection gamma H. Well, in this case, of course, you have two ends, right? But in higher dimension, you can have all of these. So let's say that we are having only Dirichlet boundary condition and Newman boundary condition. And then normally what you find in papers is that this is equal to the empty set, right? So their intersection is empty, right? Normally, of course, what you will find as well is that condition gets supplemented by saying, well, the boundary is normally the union of these two, and they are disjoint. So you cannot basically apply both. Now, since we have two ends, we can basically pick. At one end, we can pick Dirichlet, Newman, or convective type of boundary condition, mixed. And the same for the other end. So if we are prescribing only Dirichlet boundary conditions, say we want to prescribe the left end with 1 centimeter displacement and on the right end with 3 centimeter displacement, we are only prescribing Dirichlet boundary conditions, in which, in our case, gamma U, right, becomes both ends, and this is called a pure Dirichlet problem. Okay, you could apply both Newman boundary conditions only, in which case you have a pure Newman problem. Okay, and the same holds for the last boundary condition. Yeah. Correct. Yeah, of course. So you can say at the left end we're going to prescribe the displacement, and at the right end we're going to prescribe the force. That is usually the simplest problem that you will see. We fix the left end and then we apply a force to the right end. This is that type of boundary condition. What I'm saying is you cannot prescribe both because in a way the actual force in a prescribed Dirichlet boundary condition is actually the reaction force, right? So you either know the displacement or the force. You cannot prescribe both at the same time. Okay, so now we're ready to formulate the strong form of the boundary value problem. So normally you will also find this type of terminology in papers. You're going to say, well, first I need to define the quantities that are going to be involved in my equations. So given E, which is the Young's modulus, whose codomain is omega, the closure of omega to the reals, this is just very simple notation to say that this E is defined on the entire domain plus the endpoints, right? And it's just a scalar. A, which is the cross-sectional area, which is also defined in the closure of omega, and it's also a scalar. My distributed spring, which is defined in omega, look at, I'm using the open set now because I really do not need to define that in the closure. It appears nowhere in the equations of the boundary condition, so I can actually have to define that as in the closure. Then I have B, also from omega to scalars. Then, given all of these quantities, find U such that my equilibrium equation holds. And it has to hold for all x in omega. But as I said, just the equation is not enough. So we need boundary conditions. And then here, as I said, we can choose. We can say, let's say, for example, U is equal to U bar on gamma U, and then EA du dx, and is equal to N on gamma T, or we can change the second one, for example, by a convective type of boundary condition. Or there are different alternatives there. Something important to note is, say you have a pure Newman boundary value problem, right? We're not prescribing the displacement. Can you solve that problem? No? Why not? So if I prescribe a force on the left and I prescribe a force on the right, it's a pure Newman boundary value problem, right? Can I solve this problem? Huh? Well, indeed, I have to be able to do something in particular here, because you see that I'm not prescribing the rigid body motion of this bar, so it can be freely, it can move freely in space, but you can actually solve for this problem up to a constant, because you can actually obtain the state of stress in the bar, yeah, and basically still you're still unable to localize these bars in space because you didn't fix the displacement. You can actually get the stress field, but indeed you have to solve this for a particular cases when those forces are self-equilibrated, right? But it is possible. So this is the strong form of the boundary value problem here. And as I said before, depending on the type of boundary conditions, you can have a pure Dirichlet problem, a pure Newman problem, and so on. There are several combinations. So let's finish that. Okay, as we said, this has to be satisfied everywhere in your bar. And you know that for the most simplest cases, especially in 2 dimensions, this is possible, as we said, but the moment you try to change slightly the geometry of your problem, most likely you won't be able to find an exact solution. The exact solution may exist, but for our point of view, to find that exact solution may not be feasible at all. And so we need to satisfy or try to satisfy that equation a little bit less restrict, right? And so we come up with now what is called a weak formulation of equilibrium, a variational form, or as I said earlier, you can find this as the principle of virtual work in structural mechanics. So that's what we're going to do now. We're going to move away from the strong form of the boundary value problem, and we're going to try to find a weak statement of equilibrium. So I'm just going to write the same thing I just said so that it is part of the notes if you're not looking at the lecture, at the video. Okay, this is the same thing I just said. There are many ways to get your weak formulation. And most likely you have already come across this at some lecture in the past. So who can tell me a little bit how you can come up with this weak or variational form where we are relaxing the satisfying the equilibrium equation exactly everywhere, but on mostly on average. So what are the methods that you know to get this? Yeah. Yeah, that is a very good one. So you can minimize potential energy. What else? Virtual work. That is a straight. You have already the weak formulation. That is already you don't need to do anything. By minimizing potential energy, you have to take the derivative and then you obtain the expression. Anyone knows another method? Yeah. Okay. So yeah. Tell me.
No, right.
So yeah. Sorry. Perturbation techniques. I'm not really familiar with that, so I don't think. Yeah. Yeah. Those are used in dynamics, right? Yeah. So there is one more called the method of weighted residuals. So going back to the minimization of potential energy, there are many problems or differential equations that do not have a potential, so you cannot apply this principle. And if you talk about the principle of virtual work, well, most likely you are dealing with problems in structural mechanics, right? So as long as you cannot make an analogy for a different differential equation, you cannot really apply the ideas of principle or virtual work, right? And so there is a method, in my opinion, is more powerful, that is called the method of weighted residuals, and it's very simple. What we do with this method is we just take our differential equation, we multiply that by a function, right? In fact, as we will see in a few minutes, it's actually a projection that we do. We're projecting the equation in a space. We're going to get there. So we're taking our differential equation, we multiply that by a function, and we integrate over the entire domain, and we set that equal to 0. And then we're going to work from there to see what our weak or variational form of equilibrium looks like. Okay. So we are already almost in time, so let's extend a bit so that we treat the weak formulation. Okay, let me just write down the expression and then we go to the break. So what I said is we take our differential equations, right? So it's EA du dx plus B minus KU. This is our equation. And what we're going to do, we're going to multiply this by some function that we're going to call our weight function. And we're going to integrate over the entire length of our domain from 0 to L. And we're going to set this equal to 0. And this has to be valid for all W in some space of functions, right? We're going to talk a little bit about spaces in a minute. But let's call this E that is defined on that domain that is of interest to us. So this is our weighted residual. Yeah. No, that means that that space is a space of functions that are valid on that domain of interest, right? So you are not interested in anything that happens outside that domain omega because you are not seeking for a solution anywhere else than omega. So that space operates on that domain omega, okay? And we're going to talk a little bit about spaces, but since we're going to get slightly mathematical there, let's make a quick break, and then we come back to finish that part on weak formulation. Okay? See you in 10 minutes.
It's hardly readable when you halve the line thickness, because if you write with a thinner line, it's much better, I think.
You think so?
Yeah.
Okay. Okay.
Thank you.
So, question.